All right. Hello, everybody. Today is the last lecture of this mini course. So, last three lectures, actually, we have discussed about nonlinear filtering theory briefly, and we derived the corresponding filtering equations, right? Kushner-Stratnovich equation and the Zakai equation, which solves the unnormalized filter, right? So as I mentioned yesterday at the end of the lecture, in practice, we actually, most of the time, we couldn't obtain analytical solution for the filter. Therefore, we have to use some, numerical schemes to construct an approximation for the underlying filter associated with the nonlinear filtering problem. So today we are going to discuss one basic numerical scheme. Okay, so we call a particle filtering problem. So let's start to discuss that. Filtering approach. Okay. So, so in this section, we discuss the particle. We discuss particle filtering method to approximate unnormalized filter theta t, right? So we are going to discuss a particle filtering method to approximate unnormalized filter theta t. That means theta t solves the Zakai equation, right? So now recall that our filtering problem. Recall our filtering problem on the new probability space with probability measure p tilde. So do you remember that? So this is our signal process, dxt alpha minus beta h xt dt plus beta xt dyt plus gamma xt dbt, right? And also we have stochastic differential equation which solves the Radon-Nikodym derivative m tilde, right? This is dm tilde t equals m tilde t h of xt dyt. So we have this system. This is the system. Remember, this is the system we used to derive Zakai equation, right? Now, let the I runs from 1 to infinity be independent copies of B, right? Independent copies of B, right? B is the Wiener noise, right? Associate with our signal process, right? So we consider, I mean, BI is a sequence of independent copies of Wiener noise B, right? We also know that, right? Process YT, right? That is the observation process, right? YT is independent of BIs under new probability measure P tilde. We proved, right? Proof of this fact actually we discussed, right? In previous one of the previous lecture. So now we can express interacting particle system as follows. Okay, because we generate independent copies of this Wiener noise, right? Using that fact, we are going to define or construct interacting particle system, right? That is dxit alpha minus beta h xit dt plus beta xit dyt plus gamma xit dbit, and the m tilde it h of xi dyt with mi0 being 1. Because, so this is, sorry, m tilde is 0, because this is the Radon-Nikodym derivative, right? It is an exponential martingale. Therefore, m tilde is 0 is 1, right? So I answer as 1. So this is the interacting particle system. So you generate independent copies of this Wiener noise, right? Associate with our signal process. Using that fact, you can, construct or define this interacting particle system. Okay. Now let's focus on the following theorem. Okay. All right. Theorem 4.1. Okay. Suppose that initial data of this interacting particle system associated with the signal process, right? Are IID real valued, right? Real valued random variables. With common distribution y naught on R, right? Because we know that the initial value of the signal process, okay, and we assume that those are independently identically distributed real valued random variables with common distribution pi 0 on R, okay. Then the conditional expectation of the state of the signal, that is f of xt, with respect to the new probability measure p tilde, is nothing but limit n goes to infinity 1 over n of I runs from 1 to n m tilde I e f of psi t, where m tilde I t x I m tilde I n x I is the unique strong solution, let's say, oh, so this is the interacting particle system, okay, unique strong solution of the interacting particle system. So that is very nice, right? So because we have very nice assumptions regarding on these coefficient functions associated with the signal process and observation process, right? Everything are very nice, bounded at and Lipschitz continuous. Therefore, we have strong, I mean, we can verify that this system has unique strong solution, right, for each I. In that, because of that, the conditional expectation of the state of the signal process with respect to new probability measure is given by this limit, right? Right. So basically the right nth average of this, and when n goes to infinity, it actually converges to this. All right. This is good. In the finite, so when you actually restrict, so this here we have this interacting particle system. This I runs from 1 to infinity. So you can see that for when you restrict I runs from 1 to n, some fixed n, so you have finite interacting particle system, then you have actually you can represent this summation as the duality pairing of f with the corresponding empirical measure. Okay, empirical measure associated with the finite interacting particle system. So you will see that, right? When n goes to infinity, you basically approach that, you know, duality pairing or conditional expectation of your state of signal process with respect to empirical measure. Then you get certain approximation, right? For your unnormalized filter. Okay, let's briefly, you know, discuss the proof of this. Observe that IT and tilde IT right conditionally given, you know, with respect to or given the information, you know, sigma field GT, conditionally independent with identical conditional distribution. Okay. Right. These are conditionally independent, right, with respect to the information up to time t, the sigma field generated by the observation process, right? And they have identical common conditional distribution, right? Since the BIs are independent copies of the one-dimensional Wiener process B for I runs from 1 to infinity, by the conditional version of the law of large numbers, right? By the conditional version of the law, the law of the strong law of large numbers, we have limit n goes to infinity 1 over n, I runs from 1 to n, m tilde I t f of x I t. Actually, this is converge to the conditional expectation of m tilde p f of x t given gt. What is this? This is the integration of f of x t with respect to the filter theta t. This convergence holds almost surely, right? So this is the proof, just the proof of this theorem, right? So now you can see that by constructing an interacting particle system associated with the filtering problem, you can get this kind of nice convergence toward the filter, right, based on the interacting particle system. All right. So the above theorem, right? The above theorem suggests us to construct a numerical scheme which approximate theta t by weighted empirical measure of a finite system, particle system, and then each stochastic differential equation in the particle system approximate the solution by the Euler-Maruyama method. All right. So this the theorem we proved a short while ago actually suggests us to construct a numerical scheme, right? So now we have a hope because of this, right, that we can construct a numerical scheme that our unnormalized filter theta t actually can be approximate by the weighted empirical measure. Why I am saying that weighted empirical measure? Because in the empirical measure this weight appears. Okay, you will see very soon. Okay, weighted empirical measure associated with the finite particle system, right? Then at the same time, the stochastic differential equation, right? That means our signal process, right? In finite particle system, we have to discretize it, right? Discretize it, and we have to approximate the solution of that stochastic differential equation by Euler-Maruyama method. So we have to combine these two approaches to ultimately obtain certain approximation for this guy, right? Particularly theta t, right? Okay. So let's see how to execute this, right? Step by step. Okay. Now we denote, because we are going to discuss these two approaches, right, that will finally gives us a certain approximation for our unnormalized filter. So let's start to do that. Denote eta tilde I t as the integral from 0 to t h of x I s dys, right? We denote this stochastic integral with respect to the standard Wiener noise y as eta tilde it for each I, right, in our interacting particle system. Because under you already know that under the new probability measure p tilde, our observation process is standard Wiener noise, right? So we can observe that eta tilde it is a eta tilde it is a p tilde martingale and quadratic variation I'm sorry, my phone is ringing. Let me stop it. Okay, I'm sorry for that. Quadratic variation is given by eta tilde I it's nothing but h of x is square ds, right? So this is the quadratic variation. Okay, this is the quadratic variation. So you know that our function h is very nice function, right? That is associated with the observation process, is bounded with the constant k. Therefore, you can realize that this is bounded by k squared p, right? Just refer to the assumption 1.1, right? We prescribed in the first lecture. Okay. So that means it is easy to see that m tilde I t is the exponential of eta tilde I t minus 1/2 eta tilde I, quadratic variation of eta tilde I, right, is P tilde exponential martingale. Okay, so we can easily verify that, right? For each I. Okay. Now we have another important proposition. Position 4.2. Suppose that the assumption 1.1 holds, okay, then the expectation of the supremum over absolute value of this exponential martingale square, right? This is bounded by 4 times exponential k squared t for I belongs to any natural number, right? All right. Okay. So this proposition is crucial to get the error bound for the case where that empirical measure associated with the finite particle system and the unnormalized filter theta t. So you will see it very soon. So let's try to prove this proposition. Proof. So we consider expectation, right, with respect to new probability measure P tilde of squared. Okay. So this is nothing but expectation of exponential of 2 times eta tilde I t minus eta tilde I, quadratic variation of eta tilde I. So you can re-express this one as expectation of exponential of 2 eta tilde I t minus 1/2 of 2 times eta tilde I, the equation of 2 times eta tilde right. Good. Times, so I missed one term over here. We have to actually compensate with this exponential eta tilde, quadratic variation of eta tilde I tilde I t. Oh, I'm sorry, I used the time variable as S, so therefore this S. This is S and this is S. Okay. All right. So let me erase these things here. Okay. So you can just easily see this, equality. Okay. Then this is bounded by, right, expectation of exponential is minus 1/2 s, okay, times exponential to the power k squared s, because this quadratic variation is, we already discussed that it is bounded by k squared times s, right? Therefore, so you can bound like this way. And you can again observe that this is a exponential martingale. Therefore, the expectation of this one is 1. Therefore, this bound is exponential k squared s. Okay. Now, by applying Doomb's inequality, right? We could conclude the proof of proposition 4.2, right? Because we actually obtain a bound for this, you know, square of m tilde I s, right? Right? Then applying Doomb's inequality, you get this. You can get this bound, right? Expectation of supremum over 0t of this is bounded by this. Okay. So that is the proof of this proposition. So we are going to use this proposition to discuss the proof of following corollary. Okay. All right. Now, before we jump into that corollary, we are going to denote or let the empirical measure, right, associated with the finite interacting particle system theta and t as 1 over n I raised to 1 to n m tilde I t direct delta function as sitting on xi t. Okay. Okay, we take theta tn as like this way. Okay. So the empirical measure theta and t is the approximation, right? Approximation of the unnormalized filter theta t. Okay, this is the approximation, right? This is actually the underlying filter, empirical measure, in other words, associated with the interacting particle system in the finite case, right? So that means we have n number of copies of BIs, right? That we noise, then we generate, you know, in a number of signal processes, right? So that is our finite interacting particle system. Okay. So now let's focus on the corollary 4.3. This gives us error bound for the actual filter theta t and empirical measure theta nt. Okay. Corollary 4.3. Suppose that expectation of the initial data associated with the signal process is bounded, I mean, it is in L2 with respect to the probability measure P tilde and assumption, as usual, assumption 1.1 hold. Okay. Let f be a bounded continuous function, right? Then for all non-negative t, there exist, right? There exist k tilde, positive k tilde, right? Such that expectation of this error right, is error bounded by a tilde of supremum norm squared of f over n. So this is the error bound. So let's focus on the proof of this corollary. All right. Okay. Proof. Observe that the sequence of random variables are conditionally independent given the sigma field gt for t greater than or equal to 0 for any fixed t greater or equal to 0. So this sequence of random variables, right, are conditionally independent given the sigma field gt. So we know that. Therefore, we have verified that conditional expectation of m tilde it f of x it given gt is this. For every I belongs to n, almost surely, right? Right, we have this. Actually, we established this result, right, earlier. On the other hand, since theta Tn is 1 over n, this is empirical measure, right? M tilde I t over Dirac delta function standing on xit. And so the duality pairing with this empirical measure theta t n with function f is nothing but this, right? 1 over n. I run from 1 to n. Right. So we have this. So this duality pairing is this conditional expectation, and this duality pairing is this guy. Okay. Now, you can consider the absolute value of the difference and take the expectation. Right. Right. So this is nothing but this is equal to expectation of over n from 1 to n and tilde it of x it, right, minus conditional expectation of m tilde it, right, m tilde it of x given gt square, right. So basically you plug these two expressions from there, right. So this is equal to 1 over n squared and some I run from 1 to n expectation of m tilde it f of x it, right, minus conditional expectation of m tilde it f of x it given gt square. All right. So then you can apply, the Young's inequality, right? And then you will get this bound to n squared. I run from 1 to n expectation of square Young's inequality together with Jensen's inequality for this guy, okay, plus expectation, conditional expectation of absolute value of absolute square of m tilde I t f x I t gt, right? You would get this, okay? Just a manipulation, right? And since this IID, right? M tilde IT and XIT are ideally distributed random variable. So this can be bounded by, right, 4 over n expectation of, right, m tilde 1 the f of x t square. Then 1 n cancel out because they are IID random variables. You can take the expectation of these two guys, then the IIDs, then 1 n cancel out because this summation actually gone because n pop-ups outside of expectation, then 1 n cancel out, and 1 n which n that n cancel out with here, then you end up with this result, right? So this is actually bounded by, right, 4 times, you know, for n times you can take the supremum, you know, supremum over function f, right, tell infinity norm square and supremum over this exponential martingale, right? So you can have this bound. So you can easily bound this one using the proposition that we proved little while ago, right? Right, we have a bound for this. So altogether we have finally some k tilde times the infinity square of the L infinity norm of function f over n. So this k tilde associated with the bound of this, right? All right. Okay. Because this k actually, you have to keep in mind that this k tilde is actually a constant which is behave like a exponential k squared t, because you know we have some exponential bound for this term in proposition 4.2 that we proved, right? So keep in mind that the error bound for the empirical measure associated with the finite particle system and the unnormalized filter theta t has a, you know, exponential growth. Okay, just keep in mind that. All right. Now, because So we have a finite particle, interacting particle filter for this empirical measure theta Tn. Now we are going to discretize this finite interacting particle system and use Euler-Maruyama method to get an approximation for the solution of, right, of that finite interacting particle system, right? So now we apply Euler-Maruyama scheme to approximate the solution of the finite system and tilde I, it's I. So I runs from 1 to n, right? Finite system. All right. So now let positive epsilon, and we pick a small positive epsilon, and for t in between j times epsilon and j plus 1 epsilon, we set it, right, as the log of m tilde it. So we denote the logarithm of our exponential martingale m tilde it as it, and then you can introduce the discretized version of the finite interacting particle system as follows. So introduce the finite system, the discretized version of the finite system, right? Finite system we denote as x epsilon I, z epsilon I, and theta epsilon I. I runs from 1 to n. So theta epsilon I is the empirical measure of the discretized version of the finite interacting particle system. Okay. Okay, this is the empirical measure for the discretized version. So the system is as follows. It's T epsilon I equal a tilde of x epsilon I evaluated at left end point of this time interval. Okay, this is left end point. So you will notice that what is a tilde? A tilde is the A tilde is the function alpha minus beta times h, right? Okay. Plus beta x epsilon I j epsilon, right? dy t plus gamma x epsilon I j epsilon d beta dbit. So this is our signal process, right? Discretized signal process, right? And dz epsilon I t. This is the logarithm of the exponential martingale m tilde it for the discretized case. This is nothing but h of x epsilon I evaluated at j epsilon dyt minus 1/2 absolute value of x epsilon I epsilon square dt. So we have another equation for the empirical measure for the discretized version, that is theta, right? Theta n epsilon t, right? This is 1 over n, I runs from 1 to n, right? I runs from 1 to n exponential of z t epsilon I times direct delta function sitting on x epsilon I t. All right, now we have the discretized version of the finite interacting particle system. Okay, nice. So here, so I couldn't actually denote this. A tilde is nothing but alpha minus beta, right? Okay. So now we have another useful theorem, right? The following theorem discusses, right, the convergence of each particle in the finite, finite, sorry, no, the following theorem discusses the convergence of the each particle in the discretized version to the finite particle system. Okay. So let's state the theorem. All right. Theorem 4.4. Suppose that initial data satisfy this condition as usual, and assumption right? Assumption 1.1 hold. We have expectation of supremum over S less or equal to some cap T of X epsilon I S minus Xi S square plus supremum S less or T of Z epsilon I S minus Z I S square less or equal to some constant K, which is 1 depend on cap T times epsilon, right? So I want to modify this statement this statement actually this theorem actually supports to discuss, right? So we use this theorem to discuss the empirical measure associated with the discretized particle system toward the finite interacting particle, the empirical measure associated with the finite interacting particle system. All right, so let's discuss the proof of this theorem. It is also a little technical, but let's go through quickly the main steps. Then it is easy to follow the discussion appropriately for you guys. Proof. Due to discretized system, and finite particle system, right? You can immediately get that this difference except epsilon IT minus XIT is nothing but these three integrals 0 to T A tilde X epsilon I epsilon minus A tilde XIS ds, right? Plus integral 0 to T beta X epsilon I epsilon minus beta XIS square dys, that is a stochastic integral with respect to the Wiener noise y, plus 0 to T gamma X epsilon I epsilon minus gamma Xi S dB Si, right? You can immediately get this. Why is that? I have erased this, discretized version of the interacting particle system. So let me write down quickly those two equations. Then you can, see it. Let me quickly write down those two equations. First one is Tx T I is nothing but a tilde of x I t dt plus beta x I t d yt plus gamma x I t d dit, right? And the discretized version is d x I epsilon t equal a tilde x I epsilon j epsilon dt epsilon dyt plus gamma x I epsilon j epsilon db it, right? So here I runs from 1 to n, right? And epsilon in between, t time t in between j epsilon, let's so equal t j plus 1 epsilon, right? So this is the discretized version, and this is the signal process associated with the finite interacting particle system. From these two equations, you can immediately get this result. Okay. All right. So by using this equation, discretized version of the signal process associated with the discretized version of the interacting particle system, you can get this estimate, right? This L2 estimate for x epsilon it minus x epsilon I j epsilon square. So difference between the signal process evaluated at time t, right? And the signal process evaluated at the left end point j epsilon. That is what we consider here. So this estimate you can easily get by integrating this equation, right, from j epsilon to t, right? So then you would end up with, and using the fact that these coefficient functions are very nice, right? They are bounded functions because they are bounded by k, and Lifshitz continuity conditions, those properties, those assumptions you can use to get finally this estimate, bounded by 3k squared minus t minus j epsilon square plus 3k squared expectation of yt minus yj epsilon square plus 3k squared expectation of bi t minus bi j epsilon square, right? You can easily see that. All right. And on the other hand, these are, Wiener processes, yt and bt are Wiener processes, right? And with the variance, t, in particular, the variance of yt is t, right? So using the fact that this one you can bound it by easily some constant k2 times epsilon, okay, right? All right. Okay, so let me erase this. And also you have to consider now, expectation of a tilde x epsilon I j epsilon minus a tilde xi s square, right? Just consider this difference, that this is the coefficient function, one of the coefficient function associated with the discretized version of the finite interacting particle system. So this coefficient function nothing but associated with the drift term, right? And this is the coefficient function associated with the drift term in the finite interacting particle system. So you take this difference square and take the expectation, and so you can bound this one using the first of all triangle inequality. This is 2 times expectation of tilde epsilon I epsilon a tilde epsilon I s square plus 2 times expectation of a tilde x epsilon I s minus a tilde xis square, right? You have to add and subtract this term here and apply the triangle inequality, and simplest version of Young's inequality, then you end up with this, right? So now, right, so you can apply the assumptions regarding on the coefficient function, because they are elliptic continuous, together with this estimate, right? Then you can bound this term, first term associate with this inequality. So then you would get 2 times k squared k2 epsilon. Here k is the bound of our coefficient function, okay? Plus, so you actually bound this second term as using again the assumptions regarding on a tilde. Finally, you end up to k squared of expectation of supremum over S E, right? X S epsilon I minus xi x square. Nice. All right. So we have this result. Okay, so let me erase this. I will erase this also. So by following the similar steps, you can we can estimate, right, expectation of beta x epsilon I epsilon minus beta xi epsilon square, and gamma right. So you can estimate those two terms as well, right? Now, by by denoting this term, right? By denoting this term as if epsilon t let's say denote epsilon t as expectation of supremum t x epsilon I s minus xis square. You can achieve that final result if epsilon t less or equal 3t integral 0 to t of k to epsilon plus k squared f epsilon s, right, ds plus 24 times 0 to t k to epsilon plus k squared f epsilon s ds. All right. So basically, because we started with the difference of this, right? Difference of this. You can remember at the beginning of the proof, right? We have actually taken different square of the difference of this and take this expectation supremum of the expectation of the supremum. Sorry. So then after that we actually estimated these three terms, and by this expression, right? Then you plug back into that first expression, then you will end up this. So this is actually bounded by further simplification, some constant k3 which depend upon cap t epsilon plus k4 t 0 to t f epsilon s ds. So f epsilon t is bounded by k3 of cap t with this, right? I mean, you can just replace this one with cap t also. Don't worry, right? Okay. Then what would you get? So you have a position to apply Grunwald inequality to bound this guy, right? This guy. So applying Grunwald's inequality, we get expectation of supremum over T of the difference of the square of the difference of the signal process associated with the discretized version of interacting particle system minus signal process associated with the finite interacting particle system. So this is bounded by some constant k phi, which is depend upon cap T times epsilon, right? Good. So following the similar steps, right? Following the similar steps, you can achieve the same bound for Z, right? That means right, bounded by some constant k6. You can follow the similar steps to achieve this bound. Then you conclude the proof of the theorem, right? Theorem number 4.4, right? Okay. Follow similar steps as before to get. Good. Right. Now we are in the position to obtain the error bound for the empirical measure associated with the finite interacting particle system and the empirical measure associated with the discretized version of the finite interacting particle system, right? To investigate the convergence of measure valued processes, right? We use the Wasserstein metric in the space of finite measures, right? That means so we are going to study, right, the convergence or the error bound, right? Convergence of theta n epsilon t and theta n t. Convergence 2, okay, right. So we have to use this metric, Wasserstein metric, to compare the difference between these two empirical measures, okay. All right, so let us very briefly discuss what is Wasserstein metric means, okay. So let nu1 and nu2 belongs to finite Borel measures MF are right, then the Wasserstein distance, then the Wasserstein, let me spell correctly, Wasserstein distance, right, between nu1 and nu2 is given by mu of nu1 and nu2 equal supremum over P belongs to class B1 with the duality pairing of nu1 with phi. P is a very nice function, okay, minus duality pairing with measure nu2 with phi, right, with so what is this class B1? So this actually consists of functions phi such that they are Lipschitz continuous, right, with the Lipschitz constant 1 and also bounded by 1 for all so I belongs to R. So this is the Wasserstein metric, okay, all right. So you can see this here we have a duality pairing. Phi is a nice function, right, which is continuous function. So nu1 is a measure. So here we have this duality pairing. In our case, with let's say we have a filter, then you basically get the conditional expectation, right? All right, so we are in good shape now. Under the Wasserstein metric, space of finite Borel measures MF R is a Polish space. Okay, it's a Polish space. Okay. Now we have the following corollary. So let's quickly prove that. Okay. Let me state that first. All right. Corollary 4.5. As usual, assume this condition hold. And assumption 1.1 also holds for each, this holds for each I. Then there exist, right? There exist a constant C1 which is dependent upon cap T such that we have this error bound. Supremum T, Wasserstein's distance between empirical measure associated with the discretized version and empirical measure associated with the finite interacting particle system is bounded by C1t times epsilon. Okay. So let's go through the proof of this quickly. Okay. Proof. Right. So we consider this. Right. This difference for all phi belongs to the class B1. Okay. With the empirical measure theta n epsilon t is nothing but 1 over n I runs from 1 to n m tilde epsilon I t delta x epsilon I t. So this is the empirical measure associated with the discretized system, and theta n t is 1 over n I runs from 1 to n m tilde I t delta x I t. Okay. So this guy, let's say this is star. Okay, the star equals to 1 over n of sum of I runs from 1 to n m tilde epsilon I t phi of x epsilon I t, right, minus m tilde I t phi of x I t, right? Right. You have this. Okay. So by add and subtract of the term m tilde I t times function phi of x epsilon I t, you will end up with this bound. So this is 1 over n I runs from 1 to n, right? M tilde epsilon I t minus m tilde I t, absolute value of this difference times absolute value of phi of x epsilon I t, right, plus m tilde I t times difference, absolute value of difference of phi of x epsilon I t minus phi of xi t, right? So you can have this estimate. Now also note that we have this nice estimate, difference of absolute value of the difference of two real values, a minus b, is nothing but can be bounded maximum of a and b times difference of log of a minus log of b. So we are going to use this estimate to bound this guy further. Okay. So this is then bounded by 1 over n. I run from 1 to n, right? Maximum of m tilde epsilon I t m tilde I t, right? Times this. Inside the bracket we have x epsilon I t minus xi t plus, let me write over here then, log m tilde epsilon I t minus log m tilde I t. Right? Good. So this is actually, we can rewrite 1 over n. I run from 1 to n. So maximum of this, let's use this notation, m tilde I epsilon I t m tilde I t. For the maximum, we use this notation times absolute value of x epsilon I t minus xi t plus, what is log of this m tilde epsilon I t? This is the Radon-Nikodym derivative, right? Exponential martingale, and correspond for the discretized interacting particle system. The log of that we denote by z, right? Z epsilon it minus z epsilon it. Nice. Okay. Therefore, we right over here. Therefore, the Wasserstein distance mu of theta epsilon I t theta I t is nothing but supremum of phi belongs to class P of theta epsilon I t minus phi, right? So this is then bounded by, right? You can actually apply the Cauchy-Schwarz inequality and right, Cauchy-Schwarz. I'm sorry, I made a small mistakes. I forgot to mention you that up to over here, once we get this estimate, remember we had this function phi, right? Initially, with this estimate, then since it is Lipschitz continuous, right, you can actually estimate using this difference of phi of x epsilon I t of phi of x I t, right? So that step I forgot to mention, I'm sorry. Okay. So with that, finally we have this. Then by applying Cauchy-Schwarz inequality, we end up with right 1 over n of I runs from 1 to n. Oh, so, I'm sorry. Maximum other way around. Okay. Okay, I'm sorry. The notation for maximum is other way around. This way around. M tilde epsilon I t m tilde I t, right, times x. This is square to the power 1/2, right, times we have some runs from 1 to n of x epsilon I t minus xi t square plus z epsilon I t minus z I t square to the power 1/2, right? All right, so you have this. Good. So notice that we had a estimate for the square of these two difference, and we take the supremum over t, and we estimated, right, in theorem 4.4, right? Theorem number, yeah, let me remind the theorem number. That is theorem number 4.4. So you can use that theorem 4.4 to estimate this guy, right, in terms of epsilon. And also from the corollary proposition 4.4, what is proposition 4.4 mentioned? So let me remind you what is proposition 4.2. Actually associate with the supremum over this exponential martingale, right, is bounded by some exponential to the power k squared t, right? So using those two theorems, theorem 4.2 and proposition 4.2, you can actually estimate this guy finally, right? You can get some k hat times epsilon. Okay, so you can bound this, right? Now finally, all right, finally we are almost done, right? Finally we can combine both sampling error, right, sampling error, that is due to the corollary 4.3, just refer corollary 4.3, and approximation error right, approximation error, right? That is this corollary, right? That is the corollary that we proved, corollary 4.5. To get the overall error as epsilon goes to 0 and n goes to infinity. So let me quickly state that theorem. I'm not going to prove that, and then we will going to wrap up the this course. Theorem 4.6. Let epsilon equal 1 over n, and theta tilde n t we denote as, for epsilon we take 1 over n, so then we denote that as a theta tilde 1 over n for the discretized version. Okay, the empirical measure associated with the discretized version 1 over n n t. Suppose that as usual initial data finite, so I runs from 1 and assumption 1.1 holds, then there exist some constant C2 which is dependent upon cap T, such that expectation of the Wasserstein distance between this theta tilde n t and the actual filter theta t, right, is this is the unnormalized filter theta t bounded by C2 t over square root 10. Okay, so this is the result. Now I want to make an important comment. Okay, this numerical scheme is not very well behaved, so because of this reason, so let me point out that we can observe that the weights, right, what are the weights? M tilde t, I run from 1 to so on, associate with the empirical measure have mean 1 and variance grows exponentially fast as t goes to infinity. Remember, we proved that, right? That expectation of a supremum over t of the square of m tilde I t is bounded by some exponential function with time t. So you can see that it grows exponentially as t goes to infinity. What does that mean? This error bound is growing actually exponentially fast, this C2 especially, when time evolves. So therefore, this is not a very good a numerical scheme for to construct a particle filter for our unnormalized filter theta t. But there are some solution for that, like branching method and so on and so forth. So you can look for those methods in that, as I mentioned earlier, the book by J. Seong, An Introduction to Stochastic Filtering, this very nice book. So you can study those other particle filtering methods to how to overcome that difficulty and improve, right? All right, so let's stop the lecture. So today is the final day. So thank you very much for listening me for during my course. Thanks again.